January 1943, the Pacific. A U.S. cruiser fires a single shell into the sky and hits a Japanese bomber it never even aimed at. No radar operator guided it. No pilot corrected its path. The shell knew when to explode. The crew didn't yet realize it, but they had just fired the most important invention of the Second World War. A weapon so secret it was banned from use over land. A shell that could think. 3 years earlier, such a weapon was fantasy. September 15, 1940, London. Over 100 German aircraft flooded British airspace in the largest assault of the Blitz. Anti-aircraft guns lined the Thames, spitting flame until their barrels glowed. But the numbers told a cruel truth. 1,800 rounds for every aircraft destroyed. The defenders fought with courage, but they were gambling with physics. Their shells relied on timed fuses, mechanical clocks set by hand under bombardment. If the fuse ran too long, the explosion bloomed harmlessly above the target. Too short, and it burst below, wasting the shot. Every miss filled the sky with dazzling futility. Britain could match Germany in bravery, but not in precision. Across the Atlantic, American engineers were watching the carnage with growing obsession. What if they could remove chance from the equation? What if the shell itself could decide the perfect moment to detonate, guided not by time, but by proximity? It sounded absurd. Electronics in 1940 were fragile, built from vacuum tubes that shattered if dropped from a table. A fired shell endured 20,000 times the force of gravity. Enough to crush steel, let alone glass. Both British and German scientists had already tried to design a radar-triggered fuse. Both had failed, but the Americans refused to quit. At a Maryland laboratory working under the newly created National Defense Research Committee, a secret team of physicists and radio engineers began designing something no one believed possible. A miniature radar transmitter small enough and tough enough to survive the launch of a gun. They didn't just want a smarter shell. They wanted to rewrite the laws of warfare. 3 years later, their creation, the VT Proximity Fuze, would make anti-aircraft fire 10 times deadlier, devastate kamikaze attacks in the Pacific, and turn Allied artillery into sky-borne precision weapons. It would remain so secret that generals called it the Second Manhattan Project. And it began with a single question, whispered in a laboratory basement. Can a bullet know when to explode? It began not in a factory, but in silence. A handful of engineers gathered inside a converted warehouse in Maryland, surrounded by crates of vacuum tubes and the smell of solder. The war was already raging, but their battle wasn't against soldiers or nations. It was against physics itself. Their task was simple to describe, impossible to achieve. Build a fuse that could sense its target. A miniature radar transmitter, small enough to fit inside the nose of an artillery shell, and strong enough to survive being launched from a gun. The first problem was power. A shell couldn't carry a normal battery. Dry cells leaked or failed within months. Worse, they could accidentally trigger the transmitter on the ground. One electrical spark could set off an entire ammunition depot. So the engineers tried something strange. They created a battery that wasn't alive until the shell was fired. Inside a tiny glass vial sat a sealed liquid electrolyte. Harmless, inert. When the gun fired, the round began to spin at nearly 50,000 revolutions per minute. Centrifugal force shattered the vial, releasing the liquid into a stack of zinc and carbon plates. The battery woke up in flight. Power surged into the circuit, and for the first time, a shell carried its own heartbeat. Next came the radar itself. The antenna had to send a signal and listen for its echo through the same piece of metal. That meant teaching the circuit to tell the difference between what it sent and what it heard. The answer came from nature, the Doppler effect. As the shell raced toward a target, the returning radar waves shifted slightly in frequency. The engineers learned to read that change, to hear the beat note between the outgoing and incoming waves. The closer the target, the louder the beat. When the signal reached a precise threshold, the fuse triggered a final switch, a device called a therotron, a tiny gas-filled tube that could unleash an electric surge in microseconds. That surge ignited the detonator. The shell exploded at the perfect distance from its target. For the first time in history, a weapon didn't need human timing. It could sense, react, and destroy by itself. But every success brought new doubts. The fragile electronics still shattered under the violence of launch. Vacuum tubes imploded. Circuits tore free of their mounts. Every gram of weight became 20 kilograms under acceleration. To survive, each wire, each component, each grain of solder had to be locked into place, like the bones of a living creature built for impact. The engineers coated the insides with wax, tested hundreds of variations, and finally watched one shell fire and function. It left the barrel intact, transmitted, received, and detonated on cue. One of the scientists simply whispered, "It lived." The impossible had become real, but proving it worked in a lab was one thing. Firing it in combat, above an ocean full of enemy bombers, was something else entirely. And that test would happen soon. The idea worked. The circuit lived. But a working idea isn't a weapon. Not yet. The engineers knew that to change the war, their invention would have to survive something far more brutal than a test range. They had built a fuse that could think, but now they had to teach it how to survive the world. Every time a gun fired, the shell endured a heartbeat of violence. The shock was 20,000 times the force of gravity. Inside that tiny casing, wires flexed like reeds in a hurricane. Tubes cracked, solder joints snapped, glass shattered into dust. So they began the long ritual of failure. Hundreds of test firings, dozens of redesigns. They filled each fuse with microcrystalline wax to hold every part in place, melted it down, tried again. They learned that even a drop of moisture could short the circuits. That one unbalanced screw could rip a component loose before it even left the barrel. They hardened every piece until the fuse was less like a machine and more like a living cell encased in armor. But outside the lab, skepticism was growing. Some officers mocked the project as fantasy. Others feared it. If even one malfunctioned on a ship, it could destroy the entire vessel. A single spark in a hold full of ammunition was the nightmare every captain carried in the back of his mind. The War Department gave them one chance to prove it. In the winter of 1942, on the deck of the cruiser Helena, the Navy loaded a handful of experimental shells into its guns. The crew didn't know what made them different, only that they came in small, unmarked crates, and that the men handling them wore gloves like surgeons. When the enemy aircraft appeared on the horizon, the gunners fired. The first shell exploded far out in front of the target. A miss. The second burst too soon. The third found its mark. Without anyone adjusting a single dial, the shell detonated just beside the bomber's wing. The fragments tore through its fuselage, and the aircraft fell into the sea. The bridge fell silent. Then the captain simply said, "Load another." That day, the Navy recorded the first confirmed kill by a proximity fuse. A single round had done what once required hundreds. Back in the lab, the engineers waited for the message they had spent 3 years hoping to hear. It arrived by cable. 2 words. It works. But success brought a new kind of fear. The invention was too powerful to reveal, too valuable to risk falling into enemy hands. So even as production began, secrecy closed around it like armor. Only a few hundred people in the world knew what the fuse could do. Even fewer understood that this quiet, unseen device would soon decide the fate of the skies over the Pacific. And the enemy had no idea it even existed. By 1943, the secret had grown too large to hide in laboratories. factories across America began receiving anonymous blueprints divided into fragments, small, unconnected assemblies no worker could fully understand. One plant made metal casings, another produced glass vials. A third built strange, coin-sized vacuum tubes half the size of a fingertip. No single worker saw the full design. Only when all those parts met in a guarded facility near Washington did the pieces come together into the most advanced fuse the world had ever seen. Each one was inspected like a jewel, each serial number logged. If a single fuse went missing, an investigation began immediately. They were that secret, because no one wanted this falling into enemy hands. The military's first rule was simple. These fuses could only be used over the ocean. If one failed to explode, it would sink beneath the waves, lost forever. And so their battlefield became the Pacific. American ships were under siege. Japanese dive bombers attacked in waves, slipping through anti-aircraft fire that still depended on timed fuses and luck. The Pacific sky was a killing ground, where even experienced gunners watched helplessly as bombs screamed toward the decks. Then, one day, the rules changed. A fleet equipped with the new shells faced its first real test. The gunners didn't know the science inside them. They didn't need to. They just aimed and fired. When the first wave of attackers came in low, the air erupted with perfectly timed bursts. The skies seemed to anticipate the planes. Every round exploded in their path, not behind or ahead, but around them like invisible hands closing, one after another. The bombers fell, the ship's captain wrote later. It was as if our guns had learned to see. The results shocked even the scientists who designed it. For the first time in the war, anti-aircraft fire was accurate, consistent, deadly. Where it had once taken 1,800 rounds to bring down a single aircraft, now it took less than 100. A tenfold leap in lethality. In a war where seconds decided survival, that margin changed everything. Production soared. By late 1944, American factories were turning out 250,000 fuses every week. Each one was assembled by hand, tested, and packed into shells bound for the Pacific. The technology spread quietly from ship to ship, fleet to fleet, until entire naval groups were protected by a curtain of proximity fire. Kamikaze attacks that once overwhelmed defenses were now shredded before they reached the target. On the decks of those ships, gunners began to believe something strange, that maybe, at last, the odds were turning in their favor. They were right. But as the Pacific skies cleared, military planners saw another opportunity. If this invisible weapon could defend ships, what might it do over land, where artillery ruled and entire armies depended on the sky? That question would lead to the next step, one that would finally break the enemy's will to fight. For all its promise, the Proximity Fuze did not arrive as a miracle in a neat package. It arrived in the middle of chaos, and chaos chews on new inventions. The crisis that followed was not a single failure, but a stack of connected dangers: safety, supply, and the moral shock of a weapon that made war suddenly much deadlier. The first crisis was raw and immediate: safety. The fuse used live electronics and tiny charges inside shells. If a production error or handling mistake occurred, whole magazines could become killers of their own crews. Commanders imagined ammunition ships that might go up like lighthouses. For months, the Navy and the Ordnance Department treated every crate as if it contained a live grenade. Men moved them with gloved hands. Men counted them by serial numbers and interrogated any rumor of a missing unit. That paranoia slowed distribution, and delay meant lives still at risk. The second crisis was logistical. To turn a laboratory success into battlefield dominance required factories, tooling, and people. At peak, factories produced hundreds of thousands of fuses a week, But each one needed hidden subcontractors manufacturing pieces so no one plant would know the whole. Shipping was a nightmare. Every fuse had to be tracked, recorded, and escorted as if it were a state secret. When deployment finally scaled up, it did so like a slow, enormous gear grinding into motion. Effective, but messy. The third crisis was tactical and moral at the front. Imagine being an artillery officer who had learned to pray to mechanical clocks and fallible guesswork. Suddenly your shells were killing in a way nothing had before. Artillery that once punched holes in the earth now exploded in the trees, scattering lethal fragments in patterns no enemy training could reliably resist. Entire defensive lines found themselves shredded by airbursts that exploded overhead instead of underfoot. For soldiers in the Ardennes forest, shells that burst in the canopy changed the geometry of danger. No trench, no foxhole, no wooded cover was safe from the new airburst pattern. Then there was the psychological crisis that rippled through the enemy. Units used to surviving bombardments discovered something worse than direct hits, an invisible net that shredded movement and morale. During the V1 campaign, proximity-fused anti-aircraft became a curtain that stopped flying bombs in mid-course. Where Germany expected terror to force the Allies back, it found an enemy that could meet that terror with a technology that rendered it impotent. In Normandy, and later during the Bulge, artillery using proximity fuses shredded attacking columns as they tried to advance beneath tree cover. The effect wasn't simply physical. It broke cohesion, slowed counterattacks, and fed doubt into commanders' plans. There were also ethical murmurs. Some argued this was an escalation, an invention making death cleaner, more efficient. Others said that anything that reduced the need for saturation barrages and spared civilians should be welcomed. The loudest voices were those pointing to outcome. The fuse reduced the number of rounds needed to stop threats by an order of magnitude. Less ammunition expended, fewer ships damaged, fewer lives lost on the defenders' side. That calculus quieted many objections, but it didn't erase the weight of what the device did. At the height of the crisis, a single, stark fact crystallized the turning point. Weapons are not tools in isolation. They are multipliers. A fuse that thinks multiplies the lethality of every gun that fires it. The same engineering that saved a convoy could strip the mobility and morale from an enemy army. And yet, amid these problems, a darker certainty took hold. The proximity fuse would not just solve problems, it would force entire theaters of war to be fought on different terms. If you possessed it, you could deny airspace, protect seas, and make forests into death zones for attackers. If you lacked it, you faced an enemy who could see in a way you could not. By the winter of 1944, the crisis had become a strategic collapse for the Axis, a storm of precise explosions, a logistics machine churning out fuses, and an enemy whose tactics could not catch up. The cost of not having the technology was suddenly higher than the cost of secrecy. The true revelation came quietly, not in a laboratory, not in a press conference, but on the battlefield, where soldiers saw the impossible become routine. In late 1944, near Bastogne, the snow lay deep over the Ardennes forest. The German counteroffensive was grinding forward through trees and fog. American artillery units waited behind frozen gun shields, unable to see their targets. They didn't need to. They had something new in their ammunition crates. When the order came, the gunners loaded the unfamiliar shells and fired. The rounds arced silently through the gray air, disappeared into the treetops, and then the forest bloomed with light. The explosions didn't strike the ground. They detonated above it, scattering molten fragments through the branches, raining steel on every soldier below. German reports called it artillery from the sky. Veterans described entire companies vanishing in seconds, their camouflage and cover suddenly meaningless. The weapon had changed the nature of the battlefield, No longer did artillery need to guess. It could now sense, measure, and decide when to strike. That was the revelation. The Proximity Fuze wasn't a better fuse. It was an intelligence upgrade for every gun that fired it. Each shell carried a radar brain that could calculate distance and timing faster than any human gunner. For the first time, firepower had awareness. American officers realized this technology could shape more than battles. It could shape strategy. Defenses once vulnerable to air attack could now create an invisible dome of protection. Warships that had once been easy prey for dive bombers became floating fortresses. Field artillery transformed into anti-aircraft defense on demand. It didn't just destroy aircraft, it destroyed the logic of air superiority. Word of its success spread through whispers. A colonel in Belgium wrote that German assaults melted under our guns. A Navy commander off Okinawa said the sky looked alive, filled with bursts that tracked incoming planes as if guided by thought. But outside those circles, almost no one knew why. The secrecy was so strict that soldiers collecting unexploded shells were ordered to bury them rather than examine them. Each fuse was counted, each fragment accounted for. The codename VT was all anyone was allowed to say. It meant variable time, but everyone knew it stood for something more mysterious. By the time the war neared its end, its numbers told their own story. In 1940, it took 1/800 rounds to shoot down a single bomber. By 1945, it took fewer than 100. And the increase in effectiveness, so dramatic that Allied analysts compared it to the arrival of the machine gun in the previous war, and yet the engineers who had built it rarely saw combat. They watched from afar, reading the reports, counting the statistics, and trying to understand what they had made. They had created a device that gave war a new kind of precision, and precision meant power. The realization settled over them slowly, that their invention had not only saved fleets and cities, but had also changed what it meant to fight at all. War had entered the electronic age, and the world would never go back. By the spring of 1945, the war had become a laboratory of its own. Every new campaign tested not just courage, but invention. And for the Americans, the Proximity Fuze had turned from experiment to doctrine. It wasn't a secret advantage anymore. It was the rhythm behind every victory. The Pacific skies told the story best. Off Okinawa, the Japanese launched their final waves of kamikaze attacks. Hundreds of aircraft diving from the clouds toward the gray shapes of the Allied fleet. In earlier battles, each ship would have relied on luck and volume of fire, filling the sky with a chaotic storm of shells and shrapnel. But now, the guns fired with calm precision. When the first formation broke through the clouds, the air itself seemed to react. Bursts of light appeared exactly where the planes were heading, not where they had been. It looked unnatural, almost sentient, as if the ships were wrapped in an invisible intelligence that could see through smoke and motion. Gunners didn't aim to kill. They aimed to trigger. The fuses did the rest. In one attack, 2 destroyers stood alone against 150 kamikaze aircraft. Not one plane reached its target. Sailors who survived said the sea around them was littered with burning wreckage. The ships had not moved an inch. That moment marked the turning point. A weapon once dismissed as science fiction had become the shield of the Pacific. In Europe, the transformation was just as profound. The same technology that made anti-aircraft guns deadly now guided ground artillery in ways never imagined. The Battle of the Bulge had shown what airburst shells could do against troops in forests. But by the time Allied forces crossed into Germany, the technology had matured into a precision instrument. Armies began to fight differently. Commanders planned barrages knowing that every shell would find its own distance. Infantry learned that cover was no longer a guarantee. Air superiority, once a contest of pilots and machines, now included unseen circuits measuring invisible frequencies. The human reaction was complex. For some, it felt like progress, proof that intelligence and engineering could outmatch brute force. For others, it felt like the edge of something dangerous, a whisper that war was evolving beyond human control. One naval officer described watching his guns fire with perfect timing, every burst synchronized like a heartbeat. "It was beautiful," he said, "and that's what frightened me." But the logic of war has always rewarded efficiency. The fuse had become indispensable, a force multiplier that could not be ignored. It shortened battles, reduced ammunition, and protected lives on one side, at the cost of devastation on the other. By the war's final months, the Proximity Fuze had done more than defend ships and troops. It had altered the balance of power itself. No fleet, no army, no air force could claim dominance without it. The turning point wasn't just in battle. It was in belief. The Allies now knew that innovation could change the outcome of wars faster than armies could adapt. And in the corridors of command, another realization took shape. If a tiny radar brain inside a shell could decide when to explode, what else might machines soon decide on their own? The war's ending was not a sudden silence, but a slow unwinding of thunder. When Japan surrendered and the guns fell quiet, the world began counting what was left. Cities in ashes, fleets at anchor, nations exhausted, and inside locked crates across America sat the leftovers of a secret that had rewritten how battles were fought. The Proximity Fuze had been one of the Allies' best-kept secrets, protected even from their own soldiers. Most men who fired the shells never knew what made them work. They just saw results. They saw planes fall sooner, attacks break faster, and artillery that seemed to possess a strange precision. But now, the war was over, and the veil began to lift. In factories from Connecticut to California, workers who had spent years assembling anonymous sub-assemblies discovered what they had actually built. The metal rings, the glass vials, the tiny tubes, they had been part of a weapon that had changed the course of history. Many of them wept. Some felt pride. Others felt unease. Engineers who had lived under secrecy long enough to forget their own names in print were finally allowed to speak. They learned that their fragile circuits had guided victory in places they'd never see. Over Okinawa, in the Ardennes, above London, and across the vast Pacific. Commanders began to realize that this invention, small enough to hold in one hand, had done what no strategic bombing campaign had managed to do on its own. It made the enemy's air power irrelevant. Reports filtered in from captured German officers after the war. Some believed the Allies had developed a new radar network, or a kind of automatic fire control. Few could imagine that the intelligence came from inside the shells themselves. The aftermath of secrecy was astonishment. Statisticians at the War Department began to plot the numbers. In 1940, it had taken almost 2,000 shells to bring down one bomber. By 1945, fewer than 100. Each percentage gain in accuracy meant ships saved, cities spared, and thousands of lives preserved. The fuse had multiplied the effectiveness of every gun it touched by a factor of 10. But victory also brought a quieter reckoning. The scientists who had built it understood what they had started. They had proven that electronics could survive the brutality of war, that intelligence could live inside machines small enough to be fired from a gun. That understanding would not fade when peace returned. In the laboratories that had birthed the Proximity Fuze, engineers began work on peacetime applications, radar altimeters, radio guidance systems, and the early seeds of missiles that could steer themselves. The line between defense and automation had begun to blur. The world had stepped across an invisible threshold. From now on, wars would not just be fought by men and machines, but by machines that could think in fractions of a second. And it had all begun with a red vial of liquid inside a shell no bigger than a coffee mug. The soldiers who buried those secrets in the mud of Belgium, the sailors who stacked those shells on deck, and the scientists who whispered it lived in a quiet lab. They had together opened the door to a new era. The war had ended. But the idea it created had only just begun. When the last reports were filed and the last shells accounted for, the story of the Proximity Fuze passed from secrecy into history. What had begun as a desperate experiment in 1940 had become one of the quiet pillars of Allied victory. But the resolution of its story wasn't about technology. It was about what that technology revealed. The engineers who had built it gathered in Washington that autumn for a private ceremony. There were no medals, no parades, only a short speech from a Navy admiral who had seen their creation in action. He said simply, "Gentlemen, you gave us time." That was the truth of it. The fuse had bought time. Time for ships to reload, for cities to breathe, for the war to turn before it consumed everything. In the months that followed, the military began to share limited details with its allies. The British were stunned. They had once declared such a device impossible. Yet here it was, small enough to fit in a pocket, reliable enough to survive the fury of battle. German scientists, captured after the surrender, examined fragments and realized how close they had been. A different material here, a better vacuum tube there, and history might have bent another way. The Proximity Fuze stood as proof that persistence could outweigh perfection. The larger meaning emerged slowly. The war had not been won by one miracle weapon or one decisive battle. It had been won by the ability to learn, to adapt, and to build faster than fear could spread. The fuse embodied that lesson. It showed that victory was not always about more guns, but smarter ones. Historians would later call it one of the three inventions that defined the war: the atomic bomb, radar, and the VT fuse. The bomb ended the fighting with a flash. Radar gave eyes to the unseen. But the fuse gave those eyes the power to act. Even in peace, its echoes lingered. The same circuitry that had once triggered explosions now guided weather balloons, measured altitudes, and helped spacecraft land safely decades later. A weapon had quietly become a teacher. Yet behind every use, the moral question remained. Was it progress or a warning? Did giving machines a fraction of intelligence make war more humane, or simply more efficient? The men who had built it couldn't agree. Some found comfort in the lives it saved. Others saw the pattern it set, a future where the boundary between human choice and machine precision would grow thinner with each invention. But history rarely waits for comfort. The world was already racing toward jet aircraft, guided missiles, and computers that could think faster than men. The Proximity Fuze had been the first whisper of that world. A small, almost invisible device that taught humanity what it meant to trust a machine. In the end, the resolution of its story wasn't triumph or regret. It was recognition that in the darkest years of war, the fight to survive had given birth to something larger, the beginning of the age of electronic intelligence. And from that moment on, every weapon, every radar, every guided system would trace its lineage back to the same quiet question asked in 1940. Can a bullet know when to explode? The war ended with silence, but the silence was never the same again. Every veteran, every engineer, every commander carried a different version of the same memory. A moment when something small and unseen changed the course of everything. In London, the skies that once burned with the Blitz were now open and calm. In the Pacific, ships that once fought, surrounded by fire, floated in peace. And somewhere in Maryland, in the same quiet laboratories where it all began, a few engineers packed away their test equipment and sealed the last reports. The Proximity Fuze had done its job. It had saved fleets, turned back attacks, and shortened the war. But what it truly left behind was not victory. It was a lesson about the strange partnership between invention and survival. It had shown that the difference between chaos and control could be measured in milliseconds, that the right spark of understanding, placed in the right hands, could reshape an entire world war without anyone ever seeing it happen. When the scientists who worked on it looked back, they spoke of the moment that first shell came alive in flight, the glass vial breaking, the circuit humming for the first time. They remembered how they called it the thinking shell. In truth, it never thought. It only reacted faster than humans could. But that illusion of thought was enough to change the world. Its legacy stretched far beyond the battlefield. The same ideas that taught a shell to sense its target would one day guide spacecraft through the atmosphere, control the altitude of planes, and help satellites orbit the Earth. It was the first breath of modern electronics, the point where vacuum tubes learned to survive violence and carry reason into motion. Historians later called it the unseen victory, a device too small for parades, too secret for speeches, yet powerful enough to rewrite the odds of war. When nations celebrated the end of fighting, no one cheered for the fuse, but every cheer owed it something. The men who made it never claimed heroism. They built it because someone had to. Because every night of the Blitz, every bomber over the sea, every ship burning in the Pacific asked the same question: how do we stop this? And so they answered. In circuits and solder, in glass and steel, in the heartbeat of a tiny machine that could measure distance in microseconds. It didn't end the war with a roar or a blinding flash. It ended it quietly, one perfect detonation at a time. The shell that could think became a symbol of what humanity can do when cornered by destruction, when invention becomes the last act of survival. They once thought it would fail. It never did.